Hello and welcome to another design programming lecture, and this week we're going to be talking about complexity and where it can be found in both nature and in computing. So if you look up complexity in the thesaurus, you will find that its closest synonym is apparently complicatedness. But that's actually not quite true, because complexity and complicatedness are very different ideas. Have a think about this P5 sketch. This is actually one of Dan Schiffman's coding train examples. I would say it's not very complicated. It is very simple to describe. There are balls dropping down from a source at the top. They fall through a simple grid of circles and they end up in some bins at the bottom. I don't think that's very complicated. But can you predict where any individual ball is going to end up? I think it's a little bit more difficult than that. So there is some complexity afoot here. There is something that we cannot so easily predict, even though the rules governing the system are pretty simple. So complexity, as it's understood by people who study it in biology, in urbanism, and in computation, has a couple of specific differences. Like complicatedness, it has often the interaction of many pieces. But where those pieces interact in a straightforward fashion to make something complicated, it is actually the fact that they cannot be picked apart that makes something complex. Complexity can often have a few pieces, but they are inseparable. You cannot describe how one of them works without reference to all of the others as well. You just lose something in an attempt to break it apart and talk about the pieces individually. We describe these things as being irreducible. And the third property that complex things tend to have is that something can emerge from them that you didn't put there. If you have a set of rules or the description of each piece or a set of rules about how they relate, that doesn't necessarily mean that you know exactly what is going to happen. You might not be able to predict something because whole new kinds of behavior can come out of the system even with very small changes to what is going in. Another way to think about this is that a very small change to the system can end with a very big change to the output. In the natural world, we have ants. Each individual ant is phenomenally stupid. Apologies to any ants in the audience. They cannot even really comprehend their surroundings. And yet, acting together, acting as a colony, acting as a hive, ants can build bridges. Individual ants can decide, based only on the signals they're receiving from ants around them, to turn themselves into furniture for the good of the hive. Ants recognize when the pressure of ants around them requires them to try and reach an objective. They are aware of objectives only because of the scents, the pheromones that they are receiving, and they can stand themselves in the right space such that ants before and after them can continue building a bridge to the place they need to go to get food or whatever. Each ant is stupid. The hive is smart. What kind of behaviors, what kind of systems make the ant like that? And can we try and build similar things in our computational tools? I think a way to break this down, to talk about the difference between simple and complicated and complex, is to start to think about the two different axes. In the top corner, we have things that are neither complex nor complicated. They are simple. A kettle is simple. It has a heating element, water goes in, it applies electricity to the heating element, which generates heat, which is then applied to the water. Every piece of that is well understood, and there's no complicated interactions. Now, unless you maybe want to model the movement of the electrons through the element, but if you are not doing that, you're treating them as simple functional units, the whole thing is very simple. And then you have things that are not complex, but are complicated. What's a great example of that? Your taxes. Your taxes usually do not involve a lot of complexity. There's not a lot of interactions between pieces. I mean, maybe if you're Google and you're filing your massive corporate international tax situation, maybe there's some complexity with the interaction of regulations that are inseparable there. But if it's just you doing your taxes, taking some deductions for that gaming PC you bought under COVID and want to write off as a uni or work expense, normal person taxes, you fill out a bunch of pieces of a admittedly complicated and laborious form, and then once you've gone through each of those steps make sense and can be separated from the whole, you end up with a number at the end which says you owe the government money or something or other. Not complex, but certainly not simple. That gives us our bottom left. Now the top right is where things start to get interesting. What is something that is not complicated, but is complex? This is a simple system called Langton's ant. This is actually pulled from a P5 sketch. You can follow the link down the bottom to see it yourself. All Langton's ant does is it moves forward on an infinite grid of squares. And if the square it is on is black, it turns left. And if the square it is on is white, it turns right. It then changes the color of the square underneath it and moves in that desired direction. You might think that this system would be boring, that it would follow a simple repetitive pattern, but actually it produces chaos. And if you were to follow this over time, you would see that for thousands of steps, it produces no recognizable pattern. It just makes a larger and larger smudge of seemingly random, seemingly pointless squares. And then something unusual happens. We're taking this same thing zoomed out now, and look, it has gotten into a pattern. All of a sudden, after however many thousand steps, Langton's ant starts following a path of about 50-something steps, where afterwards it has moved down and to the left. If you put a bunch of random obstacles on the field for Langton's ant, it seems like it almost always ends up doing this. There is actually an open question for mathematicians. Can you prove that it always ends up making this ant's highway? This will then go on forever in this GIF. It resets as soon as it hits the edge of the sketch. But if you had an infinitely sized grid, it would just keep going now. No more chaos, just following this. Out of chaos, order. Out of simplicity, emergence. And remember, this thing has one rule governing its behavior. This ant is way simpler than those real-world ants that we saw before. This ant is chaotic in that we cannot predict how its behavior will end up, and that we cannot describe how it will get there. But it is simple. It has just one rule. It is not at all complicated. And then we get to things in that bottom right-hand corner. These problems have been called wicked problems, but another way to think about them is problems for which creativity is the best tool we have. Horst Rittel, an urban planner, wrote in the 1970s about this idea of wicked problems that are so complex that you cannot handle them piece by piece. Any proposed solution must tackle the whole thing at once, and yet at the same time, tackling the whole thing at once is so difficult that you can't even think about where to start. Examples that Rittel gave were the design of a city, peace in the Middle East, and climate change. So things that are, pretty hard. But if you look at wicked problems on a smaller scale, they're really things where there is no obvious solution. There are things where there is complicatedness, but there is also complexity. There is interaction between parts, but there are also many parts. It's those situations where we turn to creative design. We turn to the tools of human-centered design that allow us to try and find a pathway through something that is unsolvable. To give an example, let me fix my slides here. What's an example of a real-world wicked system, a system that is both complicated and complex? Well, I think probably the most interesting example that we can give is a city. A city, if you look at it at the scale of us looking at a hive of ants, a city is a wicked complex system. A city has seeming emergent structure, but that comes out of the disordered decisions of many millions of individual actors. There appears to be some emergent structure at the end, but what goes into it is often really difficult to understand. I like the idea of Manhattan here, which has two central business districts. One in the top of this picture, you can see down the bottom there, that grew up around Wall Street, that's Lower Manhattan, and Midtown, which is in the foreground here. The original reason for this is that the land in between the two was too sandy to support the foundations of early skyscrapers. That's no longer the case. You could build skyscrapers in that intermediate area, but network effects, the fact that Midtown and Lower Manhattan are already CBDs, mean that there is little reason to put tall buildings in the middle there. Out of some initial conditions, soil quality, comes emergent complexity. One example of some part of cities that is an emergent behavior is why it always seems like buses come not at all or 5 at once. Why are there always so many buses showing up at the same time? Don't those idiots at the transit department just need to get their timetables fixed? Well, no. As there are more people needing to get on a bus, the bus needs to make longer stops at each stop, just to let everybody on. And the more a bus needs to stop at a stop, the more it is slowed down relative to its original timetable. The more the bus behind it, which has fewer people, because now more and more people are getting on the first one, and suddenly the second bus is caught up with the first. And once it has done so, unless the first bus fills up, no one's going to get on the second bus, the first one is right there. So the second bus cruises along behind it, almost empty, forming a nice little convoy of buses. And you, waiting for your bus to go out and catch up with your friends, you shout at the heavens and say, "Why must I have to wait? Why are there always so many buses arriving together? Why couldn't there have been one bus every 10 minutes? But your enemy today is not the state transit department, but complexity. The buses clumping together are an emergent property of roads and waiting times and the nature of bus stops, and not anything that TFNSW can fix. So that's enough, I think, about complexity in the natural world. I hope I have inspired you to think about how properties of complex things can come from relatively simple origins, but lead to hard-to-predict behavior. Now, why are we interested in this as folks doing a creative coding subject? Because one of the most fun things that we can do in creative code is produce complex emergent behavior. This is a set of flocking behaviors. These are boids or bird objects originally proposed by Craig Reynolds and re-implemented here in part of the P5 examples, I believe inspired by a sketch from Dan Schiffman originally. Reynolds was attempting to imitate the flocking behavior of birds. These objects follow 4 simple rules. They stick together, they try not to bump into each other, they try to be going towards... Oh no, these ones are 3 simple rules. They stick together, they try not to bump into each other, and they try to be going in the same direction as the boids around them. The 4th objective that they can have is to follow a target, but these ones aren't doing that. There's not that much code here, and yet it produces these complex, I would say beautiful, flocks. You can see me adding more with the mouse there. This is a recording, not a live sketch. But as soon as they are created, they go out in random directions, but they immediately align and start following a similar pattern as the ones around them. They don't end up spreading out all over the sketch, all over the canvas, sorry. They end up clumping together and following random but structured. There is an emergent order out of their behavior, even though each individual boid is doing very little. Think about these kinds of patterns as you start thinking about your final 2 assignments. If you can come up with something that requires relatively little code but produces emergent behavior, you have a really interesting vehicle for a generator. If you want to increase the expressive range, the capacity of your generator to do different things, then having emergence as a weapon in your arsenal gives you a much greater capacity to effect a change in the output from only a small change in the input. But maybe the most famous example of emergent complexity is John Conway's Game of Life. Sounds like a funny board game that you might find an old copy of at your grandmother's, but the Game of Life is a simple 2D grid, infinite again, where there are rules for each step about what cells are turned off and what cells are turned on. I'll show you those rules on the next step, but look how chaotic yet ordered the output of this grid of squares seems to be. You seem to have some idea of areas of activity and areas of no activity, but it's very difficult to predict what's going to happen. Sometimes it disappears, sometimes it leaves these sort of lip shapes, sometimes it leaves blocks, sometimes it seems to shoot off a little glider in some direction. It's almost impossible to figure out exactly what is going to happen next. Here are the 3 rules for Conway's game of life. They have live and dead cells, represented here as black and white. Conway was interested in exploring artificial life, things that would behave in a life-like fashion, growing, dying, reproducing, suffering from underpopulation or overpopulation. It was from that metaphor that he started creating this game. So any live cell, any black cell, with 2 or 3 adjacent live cells survives unchanged into the next generation. Any dead cell, that's a white cell, with 3 live neighbors becomes a live cell. That's to impersonate reproduction. If there are 3 living cells around you, the population grows. Any other live cells, that is those with 1 neighbor or those with 4 or more neighbors, die through underpopulation or overpopulation. And all dead cells, those where there is no current living creatures, they stay dead. So the only way you can make new cells is if there are exactly 3 live neighbors. And the only way you can keep cells is if there are 2 or 3 live neighbors. Simple, right? And yet it can produce a fascinating array of patterns. Here's one example. This is called a blinker. If you just put 3 cells in a line, then they will oscillate backwards and forwards between vertical and horizontal forever, because the middle cell always has 2 neighbors, but the ones on the outsides disappear after each step, but they create the ones opposite them, which then live for 1 step and flicker back. An even more interesting pattern is the glider. This pattern of just 5 cells moves. It flies forward infinitely. It's almost as if that square at the back is propelling it like an engine. It pushes forward that little row of cells in a self-perpetuating way. This glider will go on forever. And then there's designs like this one. While seemingly the same size as the other designs on the previous slide, this pentomino will generate a seething mass of chaos that lasts for about 1,100 steps before settling into stability. Here's a little video of what the F pentomino actually produces, scaled out so that we can see what's going on. Just from that shape at the start, we see this. We see a hive of activity throwing off those little glider things that burst off forever in different directions. But I don't count those in the 1,100 or so steps of activity. Those are just predictable. But how long does it take until there is no more chaos in this system? Well, just when you think it's going to die out, it blooms into activity again, sending these things bursting across the area, picking up some of the dead scraps from earlier and interacting with them in ways that are impossible to predict. Mathematicians use this as a plaything. They use it as a way to explore proofs or find new cute gliders. You look up Conway's Game of Life and they're online, and there's a community of people who are like, I found a new left-right oriented diagonal spaceship breeder glider. It's a wild ride. But maybe you don't have to go that deep. Maybe for your projects in this unit, for your exploration of the creative capacity of code, it is necessary only to think about some of the sources of complexity that you see in the real world. Think about plants, think about cities, think about ants, think about networks of global trade, think about social networks, think about your own body and the biology of your digestive system. Many of these are complicated, but many of these are complex, wicked in their complexity and their irreducibility, but also beautiful in their capacity to create emergent form. And as you explore what you can do as a coder, think about how you can create emergence. Think about how you can create systems where a small change to the initial settings can produce a large change in the output. Explore some of these examples that I've linked here. You can find them in the P5 example set, or you can Google things like artificial life P5.js and see what you can come up with, and see how you can incorporate some of these ideas of emergence and complexity into the work you do for this unit. I'll see you in class.